Welcome back. My name is Adrian. I'm the computer science guy, and I wanted to take a step back from the details of implementation of Java and all that to give you a sense of what computer science is in a nutshell, and I'm going to go over what it takes to get a degree in computer science. So, recall that computer science is the study of algorithms, and informally, an algorithm is just a series of steps that tells you how to accomplish something. And it's similar to following a recipe. But in a formal sense, I got this quote from Wikipedia: an algorithm is an effective method that can be expressed within a finite amount of space and time and in a well-defined formal language for calculating a function. Now, what this means is that a program, which is something that's written in a well-defined formal language to calculate a function, is an implementation, an instance of an algorithm. So, one of the skills you're going to require as a computer scientist is to be able to solve problems. Now, you'll be given a bunch of sample problems in the degree in your studies, and some of them are actually well-known problems. For example, sorting. Sorting is a problem you're going to have to encounter several times, and there are well-known solutions for sorting. So, whenever you encounter a sorting problem, you're going to say, I know how to sort this, and I know several different ways to sort it. So, that's one of the neat things about a degree in computer science, because you'll be exposed to these problems that we know have certain solutions. And then anytime you see one of these problems or something like it, you can adapt that well-known solution to meet your needs. You might also encounter a whole slew of problems, and you can't solve them all at once if you tried. So what you can do instead is break down that big problem to a set of small problems and solve those individually. Sometimes it's a very useful skill, especially if the big problem is defined as an instance of the subproblems. It's called recursion, and it's a useful tool. And then you'll also come across problems that don't have a solution. And it's not uncommon to find a problem that doesn't have a solution. Especially if you're taking calculus, you'll know there are problems that don't have solutions. But when you encounter this problem, you can say, hey, this problem doesn't have a solution, instead of spending hours trying to find a solution that doesn't exist. And we can prove that this problem has no solution, by the way. But what you can do instead is you can say, hey, a person that needs me to solve this problem has a solution, but I can add some constraints to it. I can say, I only want a solution that is positive, per se. And I may be able to find a less than optimal solution, but it's a solution, and that in some cases that's good enough. So another skill that you'll be taught is automation, and that is really identifying inefficiencies and correcting them. In essence, computer scientists are lazy. So if you see the exact same sequence of code in 5 different spots in a program, I'm a lazy computer scientist, and I'm going to know it's going to be a terrible thing for me to maintain that code. So if a year from now I need to update that specific portion of code, I need to do it in 5 places. And what are the chances I'm going to remember it's in 5 different spots? I'll probably do it in 4 spots, and then no one will know there's a bug in the code until something happens, and I don't know, somebody doesn't get paid. Ugh, that would suck. So, computer scientists will say, hey, I'm going to take this exact same sequence of code, I'm going to extrapolate it from those little sections that they're currently in, put it in its own little spot, and anytime anyone wants to reference that section of code, they're just going to reference it directly. And anytime I need to update that section of code, I'll just update it in one spot, and the changes will propagate to all of the other spots. So that's one other useful skill. And another one is working at different layers of abstraction. And what I mean by that is, an abstraction of something is a model. And a model is something where it's representative of the space that you're trying to model, except it hides certain details, and that can be a lot of details to get to the big picture, or it could be a model that's close to what you're referring to, but some of the minor implementation details are missing, and that all models are wrong. One of my computer science professors told me this. All models are wrong. Some are useful. So when you design something and you make a model of it, it's a one layer of abstraction, right? Because you've hidden details. So you need to be able to work at the layer that hides lots of the details and the layers that are in between that and all the details. So one other tool you'll need is critical thinking, and that is looking at a problem and examining all aspects of it, per se. So let's say your problem is writing a grade book, and you know that it is universal truth that no grade can be less than 0 and more than 100. So if someone enters in a negative score, your program should do the right thing and say, hey, buddy, user, you've entered a negative score for this entry here. If you didn't think about that, and you just said, my program can take any number for a grade, then that's wrong. So that might not seem like a big thing, if the person puts a -1 for a 0, it's both a bad score. But if a person puts -1 for all the entries and the gradebook at the end of the semester has a negative score, something bad happened. So you want to think about that. And one other useful thing that a computer scientist should be able to do is you should be able to work with others, get along well. It is very rare to have a computer scientist in the dark basement corner somewhere working by themselves. You'll work with a team. And that team may not even be other computer scientists. That team may be made up of a whole bunch of different disciplines. And you need to be able to work with them. So if you have issues with this, you might want to kind of work on your team building skills there. So I want to show you a sample degree plan. And this is an ABET accredited school with a 120-hour degree plan. And that's only because this was in Texas, and Texas law said no degree should be less than 120 credit hours. And it was also a school associated with ACM, which said that no degree associated with ACM should be less than 120 hours. Go figure. I'm going to first show you the math courses, and they're listed here: Calculus 1, Calculus 2, Discrete Mathematics, Matrix Algebra, Numerical Analysis, and Statistics. That's not uncommon. You'll find degrees of freedom in different schools. But yes, you generally will take Calculus 1 and 2. You will take Matrix Algebra, some sort of numerical mathematics class that looks at how computers do math. And Discrete Mathematics, looks at set theory, number theory, form proofs, graph theory, all that jazz. And Stats is just was required to round out our degree because normally you don't actually ever take a calculus-based statistics class, and it's kind of enlightening. So the classes here on the left are required by the degree for graduation, and then the ones on the right are required as well, but they're optional in the sense that you can take any 5 of them. So computer science 1, 2, and 3, or introduction to computer science, elementary data structures, and data structures are the leveling courses, and this is because this degree was associated. This department was in the College of Engineering at this university, and the College of Engineering said you need to have 3 engineering leveling courses before you can take any of the other required courses. So you'll notice after you take data structures, all the rest are junior, senior level classes, 3,000, 4,000 level classes. And so in intro, elementary data structures are the first basic videos that are going to be on my channel. I'm going to cover a bunch of those topics. And then we can branch out. We can cover object-oriented programming. That's a lot of fun. automata theory, that is what can be computed. Design and implementation of programming languages. You may not think about what does it take to write a programming language. And you may also never think about can you prove that the programming language is correct and computable. Computer architecture and design, very useful course. The computer is this little box. It can only do basic math, add, subtract, multiply, divide. It can copy stuff to and from memory. It can also do ANDing and ORing, and that's about it. Bit shifting. So you might never consider what happens, in the CPU, but especially when you get to operating systems, you realize that if you're going to simulate having two programs run at one time, you may have race conditions. So that's a useful course, as well as operating systems. And then, of course, software engineering, which is computer science is a relatively new field, and unlike lots of other engineering disciplines, there are well thought out templates for how to do stuff. Like, let's say you're a civil engineer, and someone asks you to build a bridge. Say, okay, what are the dimensions of the bridge you want? And I can just go to my template of bridges, select A, B, C, or D for the design you want, put it in the computer, model it to make sure it fits within the parameters, and done. I got your bridge. There's a separate type of engineer that says, hey, yeah, this bridge isn't going to work. I'm going to need to design a real bridge that doesn't work with these parameters. And that's the type of computer scientist. That's the type of designing that you have to do with software engineering, because we don't have the standard template for building a bridge. It's not that well known. It's a relatively new discipline, software engineering. So then let's talk about the other courses here. Computer architecture 2. Everything you learn in computer architecture is a lie, because it was a model, it was an abstraction of how a real computer works, and here's really how a computer works. And then you can take other courses such as computer graphics or computer networks. That's lots of fun. Human computer interaction. A topic that a lot of people think of when they think of computer science is, how do you build a computer such that humans can use it? I mean, a lot of people claim that Windows is hard to use and Apple so much easier. Why is that? Artificial intelligence, huge subgenre of computer science. You can major in artificial intelligence, and even then you'll major in a small part of artificial intelligence. Database management, if you're going into industry or government and you want to be a computer scientist, that's a useful skill to have, especially because lots of industries run on databases. Computer security, lots of fun if you want to learn how to break into computers. Purely to know how to defend against it. Of course. Compilers. It's a class that's not often taught, at least at my university, but it's a fun course, especially if you want to learn how you get from that high level language to that low level language, and all the steps it requires to get from A to B. Although it doesn't have to be a compiler per se, you can also write a translator or an interpreter. Lots of stuff in there. And then topics in soft computing and special topics are courses that come around once in a while when a professor feels like they have enough of an expertise in an area to create a course that's not one of the listed courses. And you may find that course taught once every 10 years or so, if the faculty member is even still there. And that'll be something, really specialized subtopic, like parallel computing on GPUs, or parallel computing on supercomputers, or voice interactive systems, things like that. Those can be lots of fun. But if none of those suits your interest, you can always contract an individual studies with a professor. Say, hey, Professor so-and-so, I took your course in automata theory and I really loved it. Or I took your course in graphics and I want to do a big project like X. Or if you need something done for your research area, or I can do research in that topic for you. That's one of those you meet with the professor and you decide on what you want to do. And one nice thing about my university is they also offered an internship course. Let's say you went off on an internship in industry, but you still need to be labeled as a full-time student or something. They will let you take the quote-unquote internship course, which will keep you registered as a student while you're away on your internship, which is kind of nice. So, if you want to prove that you're a human that listened to this course, the word of the day will be automata. And in case you missed how that's spelled, that is on the left here on CS 3350. AUTOMATA. And if you have any questions, feel free to ask in the chat, in the comment section below. And thank you for watching. I look forward to seeing you next time. Bye bye.